All right. Welcome, everyone, to tonight's 60 Minutes in Space. Throughout the program, if you have any questions, please pop them into the chat, and we'll have some time at the end. I'll keep track of all those questions for you so we can pass them over to Dr. Shenoy. And speaking of, I'd like to introduce tonight's presenter. This is Dr. Sachin Shenoy he's a research scientist at the Space Science Institute in Boulder. And thank you so much for joining us tonight, Dr. Shenoy.
Thank you. Thank you for having me. I hope everyone can hear me and see my screen. I should say this is my second time that I'm presenting this 60 minutes. I did one last year where I talked about discovery of water on moon using SOFIA. So this is my second time, so I'm excited. I mean, I wish I could do this in person at the museum, but hopefully soon we can do that, and then it'll be more exciting because I really don't like sitting in a place and giving a talk. I'd rather stand and talk and gesture and see how my audience reacts. But well, we do the best we can. All right. So what are we talking about today? So I picked up two topics that I thought was interesting that happened recently. One was the first discovery of a spin of an intermediate mass black hole. Why this is important and what is this intermediate mass black hole? We'll go through that in detail. And as Mitch mentioned earlier, if you have questions, put it in the chat. He'll ask me now or at the end of the talk. The other one that I'm going to talk about is, of course, SOFIA, because I work on SOFIA and I'm excited about talking about SOFIA. So I'll talk about SOFIA, but we'll look using one of the instruments, SOFIA, at the Orion Nebula. And the reason I picked this is the data set is spectacular, one of the best we have taken. But not only that, but everyone knows about Orion. And it's interesting to talk about an object that has been observed for the last 400 years since we know about modern astronomy, and we are still learning new things about these things. Okay, so here we go. So if you peeked at the news this week, then you may have seen a online thing like this. Shredded star reveals elusive middle mass black hole. Or you may have seen something like, this is what it looks like when a black hole snacks on a star. They always come up with this interesting, attention-grabbing stuff like snacks on a star. I don't like that thing. No, black hole don't snack on a star. It's a physics that happens and the material from the star flows in. So that's not true. So what does science tell us? So let's first start with black hole. I'm sure most of you know what a black hole is, but I thought I should start with the basics, give a little bit about historical context of where this word black hole comes from, and then go from there. So in 1916, Einstein found his general theory of relativity, which talks mostly about how space-time is one. It's a space-time continuum, how gravity works with it. And the story goes that once he finished his thesis about general theory of relativity, he sent it to his colleague and friend Carl Schwarzschild. And in his description, he had an equation that needed a solution. And it's said, I don't know if this is true or false, but Carl Schwarzschild solved this field equation within a week and sent the solution back to Einstein. And one of the part of that solution was that if there is a mass of a star or any object that is really, really, really big, then its gravity is so much that nothing can escape it. Everything goes down. Even light cannot escape it. But as you'll notice, after that, for a long time, nothing happened because we couldn't see this. We couldn't detect these sources because nothing escapes it. So in 1964, some of the data from sounding rockets that use X-rays to look at the universe showed the first brightest X-ray object in the sky, and that is called Cygnus X1. And what the researcher found out that time is that the X-ray coming from Cygnus X1 not only is pretty bright, but it used to vary. And using that variation, they could figure out how big or small this object was that was giving out these X-rays. And they found that the object was very tiny, way smaller than a normal star. And in those days, of course, they didn't know that there could be an object so small that is smaller than a star, but is throwing out so much X-rays, which is the most energetic light or electromagnetic radiation that you can see. 6 years later, NASA used the data from Uru, the X-ray Explorer satellite, and that was a much better instrument and did a very detailed observation of Cygnus X1. And that's when they figured out that the source is a black hole. So in 1971, when the paper came out about the X-ray data, that's when people start claiming, okay, we have discovered a black hole, and this was in Cygnus X1. And of course, we can't see these things. These are all either in high energy X-rays and stuff. But using the data from then, we can visualize how it looks like, and it looks something like this. So Cygnus X1 is a binary. So there is a large star, which you can see on the right-hand side of your screen, and the black hole sits in the center. And what happens is these two objects are rotating around each other, revolving around each other. So the material from the star starts flowing into the black hole. And whenever a large material or cloud of gas and dust collapses onto something, it always flattens into a disk. That is to conserve angular momentum. So this material starts forming into a disk, goes around in the disk, and then falls down onto the black hole. When it falls down into the black hole, it generates this large X-ray, which is what we see. And since these happen episodically, we see the variations in these X-rays. So this is what we think Cygnus X would look like today if we could see it. So how do we make a black hole? That's all fine. Like this is great that we have a black hole, but how did this come to be? And to tell you that this is my one slide where I can talk about the entire history of a star. In fact, this would be injustice. I would have to spend hours and hours just on one part of this cycle, but I try to compress it since we are more interested in the discovery of the intermediate star mass black hole and not the life cycle of star. Maybe I'll give this talk some other time. So what happens, we start with the stellar nebula. This is the cloud of gas and dust, which you have seen in many images, the places like Orion, places like Taurus. Here in these gas of cloud, this is dynamic. It's not static. So the gas and cloud is moving about. It's chaotic. It's random. But in between these cloud, you start making clumps. When the clump happens, it has mass, so it has gravity. So the clumps start growing bigger, and that's how a star is born. All the gas and dust collapse into one object. The objects start rotating. We get a disk, and that's how stars are born. And this is what the yellow and the blue blob is showing. The yellow is a star that is an average star. Its mass is comparable to the sun, maybe a few times larger than our sun. The other thing are massive stars. These are the stars which are 10 times, 20 times, 30 times more massive than our sun. The life history of these stars are very different. The average star stays in this phase, burning hydrogen in the center to create helium and giving energy out. That's what creates the stars alive, stars glowing. And that stays for a long time, for billions of years. So for example, our sun is in the midway of its what we call main sequence. And we have another 5 billion years before the sun becomes a red giant. So this stage happens when all the hydrogen in the center of the star is converted to helium. And now there is no fusion that is pushing the energy outside, keeping it in a steady balance with gravity, which is making the star go inward. So that's why it starts growing. It becomes big, it becomes red. And in this stage, helium starts fusing into carbon, and we get more light. So this is how the evolution of a normal star proceeds. And once you have that, once we combine carbon into nitrogen, nitrogen into oxygen, so on and so forth. We create all the elements inside the star. And in the end, we are left with the core is left of iron. When you have a core of iron, iron cannot fuse into anything else. That's its end. So that's when we get an explosion. We have a planetary nebula, and the leftover is usually a white dwarf. Whereas if it's a massive star, after the red supergiant stage, there is a supernova. It explodes much more catastrophically. And depending on the mass, it can either turn into a neutron star if it's a smaller mass, or turn into a black hole if it's a bigger masses. So this is basically how you'll find a black hole. A massive star, a really, really massive star compared to our sun, goes through its life cycle, a supernova explosion occurs, and all the matter falls down into itself, and you make a singularity. And the gravity of this object is really high, so nothing escapes out. All the matter goes in, and if a light passes close to this black hole, then the light will go inside. It can't pass through. Okay, so this is called a stellar black hole because its mass is between, say, about 3 to 10 solar masses. And this is how black holes are classified now. We have a few dozen examples of each, except for supermassive black hole, which I'll talk in a minute. But stellar mass black hole, the story that I told you here, these are usually between 3 to 10 solar masses, or maybe even to about 100 solar masses. The symbol that we astronomers usually use for this is solar masses denoted by a italicized M with a circle and a dot in here. So if you see this in the rest of my talk, all it says is so many times the mass of the sun. So that's all the solar mass means. So we have seen this black holes like Cygnus X1, but there are also supermassive black holes, which you may have heard. These are at the center of the galaxy. In fact, every galaxy in our universe has a supermassive black hole in the center. And their mass can vary anywhere between a million solar masses to about 1 billion solar masses. And these are gigantic. And for the longest time, these were the two classifications we had. We had the stellar mass black hole, we had the supermassive black hole. But in the recent times, people have started discovering masses between these two extreme masses. And now we have something we call as intermediate mass black holes, which range in the mass from 100 to 1,000 to 10,000 solar masses. So today we'll be talking about one of these things. So do we see, is there any other way of seeing the black holes other than just X-rays? Because X-rays are hard to detect. We need specialized instrument up in space. Are there other ways we can look at black hole? And there is, and this is a fantastic experiment done by researchers from UCLA, where they observed the center of our galaxy, where we know is a black hole now. But this is the research that provided the evidence that there is a black hole. They looked at the center of the galaxy, which is denoted by this star symbol here, and they used the Keck telescope, and they were observing from 1995 to 2016, almost 20 years, to track each of these stars. These are the stars observed in the infrared, so they appear like a small dot, and they observed this. Let me see. Give me 1 sec. There you go. So this is real data, right? These are real stars going around the center of our galaxy, and you will see that there are dotted lines. That means the orbits were uncertain, but when the orbits became certain, we have a solid line. So this is a measurement of stars moving around in the center of our galaxy for about 20 years. And what you'll notice is this, especially the star S02, has gone multiple times around the center of the galaxy. So this is a very well measured object. And once we have these measurements, it's pretty straightforward to use Kepler's law to figure out what is the mass of the object that this star is going around. And the mass of that object comes out to be about 4 million times the mass of the sun. So that's how we know that there is a black hole in the center of the sun. an object that is 4 million times the mass of the sun in a very, very small in very, very small location in the center of our galaxy. We now have other evidence too. Recently, there was a telescope. There's a consortium of telescopes called EHT, Event Horizon Telescope, and they directly image the black hole at the center of the galaxy M87. And this is what the image looked like. One should realize that this is an astronomy image. So the color is a false color. It's not true color what you would see, because the data they use to get this image is in the radio wavelength. So these are radio data collected from the black hole, and the image was a composite of it. Event Horizon Telescope is a collaboration of about a dozen radio observatories all over the world. So when we observe this, it's like using the whole Earth as a telescope to observe it. This is one of the most beautiful images I've seen in the last couple of years, where there is a direct image of the black hole. And the black hole is the one that is dark in the center where nothing happens and the material is falling down. And these bright objects are not an artifact. It's just the fact that the material is moving here so fast, it's almost relativistic speed, which means it's moving as close to the speed of light. And these are the regions where the material is coming towards us. So there is an enhancement in brightness. So that's what you're seeing here. All right, so this is the paper that I want to discuss today. So till now, it was all about what a black hole is and can we see them. But this is the paper I'll be talking today about the intermediate mass black hole. And the researchers here are from University of Arizona, and they measured mass and spin of the black hole. And I'll talk to you about what this means. So this star, we'll start calling them IMBH, that is intermediate mass black holes. It has a designation, and that's the number up here. This is it's in a star cluster in a galaxy that is about 715 million light years away from us. It's in the constellation of Aquarius, for those of you who have gone out and observed the constellations at night. Most of the time, these kind of objects are hard to detect because they are, as you know, they don't emit anything. They're kind of dark in the visible, so you don't see anything. But fortuitously, this object passed close to a star, and it pulled the material from the star. Not only that, it basically ripped the star apart completely, and all the material from the star started falling into the black hole. These events are called TEDs. TDEs, that is tidal disruption events. And the team used 12 years of data that is observed from two spacecrafts. One is XMM Newton, and the other one is Chandra X-ray Space Observatory. So again, there is a image you must have seen this in the past. This is how it looks. So originally there is nothing much going on. There is just a small black dark object you're seeing here. But as the object is moving around in its galaxy, it came across a star whose path crossed it, and it started disrupting the star. And all of the star material flows down into it. It forms into a disk, a very thin disk, and the material slowly starts falling in. And as the material starts falling in, you'll see this blue thing coming out. That's basically the X-ray data, that is X-rays that are emitted. And the object will also have outflows on the poles, and those are the two things you see down here. So since this is a talk about science, let's look at the real scientific data, what they found. So they looked at this object, as I said, between a span of 12 years in 5 different epochs, 5 different time. And the top 3 shows the data from the XMM Newton, and the bottom data shows from Chandra Observatory. And you can see the time or the month they have observed these things. All these small data points are the measurements, are the X-ray measurements that is taken from this object. The different color just indicates that they are from different detectors. The Space Telescope Newton had 3 different detectors. So those are the 3 different colors you see, red, blue, and green. what the team did was really spectacular is that they modeled this whole event. They modeled how the black hole ripped the star apart, how it became a disk. They modeled how the star looked like before it was ripped apart. Then they modeled how materials, when it falls down, how it varies and gives out X-rays at different times. Excuse me. So those are all the dotted lines that you see. So this dashed line that is here is the disk that is emitting the X-ray, and then there are other things like what the stars look like and what the flares look like. So when you take all of those things and combine them together, you have a composite model, and that composite model is represented in this plot by the black line. Oh, before I forget, on the y-axis here, we are plotting how much energy is coming out, in each, each wavelength, and on the x-axis, we are basically plotting the energy of the X-ray, the photon energy itself. So that's how this looks like. So the model is, so they built a model and they did it, but this is great. So what does it tell me? So if you take a difference between the data of what we observed and what the model predicts, that's what is plotted on the bottom here. It's almost close to zero with about little bit of errors. And that is what that tells an astronomer, is that the model is a very good fit for the data. So the model must be close to what really is happening. Now, since this is a model, there are some assumptions that they make. So they can change the assumptions, and depending on what assumptions they make, they get different results of how big the disk is, how small the disk is, how fast the black hole is rotating. So another way of looking at it is, because you can do assumption and run a lot of these models, we can predict what the best should be. So here what is predicted is mass of the black hole. If I take different models, what does the mass of the black hole looks like? And on the y-axis is the spin of the black hole. The spin of the black hole can be 0, that it's not spinning at all, or it could have a value of 1, which means it is spinning at a maximum amount possible. And the colors here denote how good or bad your fit is. If you are in this green region, then your models are not fitting very well with your data. But when you go down here to the white box, that means your fit is much better. So that's how they found what was the mass of the black hole and what was the spin of the black holes. So, okay, fine. So what's the big deal? What did they find? And they found that regardless of how they modeled these things, the mass of the black hole always came, it was always less than 22,000 times the mass of the sun. And that puts it in the range of intermediate mass black hole. They also found that if they use their best model predicted that the mass should be about 17,500 times our sun, and the spin is about 0.8. So what's the big deal about the spin? Why should I care about it? The spin is very characteristics, and it tells about how this black hole was formed. And as you may have heard that recently LIGO has been detecting a lot of gravitational wave from the collisions of two black holes, mergers of two black holes. And we have about a dozen measurements of these merger black hole. When we merge this black hole and then you look at the spin comes out to be about 0.7 and not 0.8. So that suggests that the black hole that we have been seeing, the intermediate mass black hole that we have seen, is probably not due to the merger of two stars. What other things can happen? We can also have a case where the black hole was created like it was shown in the cartoon above, and then it started getting gas and dust once in a while. Like whenever it came close to a cloud, it will grab that gas and dust. If that happens, then its spin is very low. So it's about 0.2 or 0.3, again, not close to 0.8. Now, on the other hand, if there is a continuous infall of material from the interstellar medium onto the black hole, then the spin is close to maximum, it's close to 1. So this point, that detecting that a spin is 0.8 is a mystery. So we don't know what happens. But there are some guesstimate. If you ask the researcher, they'll say, this could be possible that if we have a cluster of stars and there is a lot of stars falling into the black hole, then maybe we'll get the spin about 8. But there are other explanations too. For example, if we have a pristine cloud of gas and the whole cloud is so gigantic that it implodes, you can make black hole again, which will have a spin of 0.8. So, but this, we don't know if those scenarios are correct or not. So we need more data. Excuse me. We need more data to figure this out. And the data will be coming soon because there is another space telescope called eRosetta that has already started looking at tidal disruption events. So keep your eye out, and you will probably in a couple of years you'll see more data, and then we can confirm or disprove that this is the spin is correct, and the spin will show us whether which of these evolution scenario is true. I can stop here now and take questions on black holes if people have it. Otherwise, I can continue with the next topic.
Well, we did have one question about stars. What's the distribution in the universe of average stars versus massive stars?
That's a very good question. So when a large cloud of gas and dust makes a cloud, most of the stars are smaller masses. Many of them are sun-like stars. There are very few that are really big O-type stars. So if you look at the distribution, it's a continuous distribution going all the way from smaller than sun to about 60 times the mass of the sun. And the distribution looks like a lot of low mass star and fewer O-type or B-type or bigger stars.
All right. And so you're about to talk about Sophia. Someone was wondering what it stands for, but I'm sure you'll get to that.
Excellent. So let's jump right into it.
All right. And we'll come back to, there's a few more questions about black holes. We can come back to them.
Okay, sounds good. So the next one I want to talk about, Sophia revisits Orion molecular cloud. And as someone asked me, what is SOFIA? So SOFIA stands for Stratospheric Observatory for Infrared Astronomy. And of course, everyone has heard about the Orion molecular cloud. I don't need to introduce anyone to Orion molecular cloud. Just to, again, build up on some basics, here is the constellation of Orion in a visible image, and you'll see all these stars. I have drawn this stick figure so that it looks like a hunter from Greek mythology, but this is where Orion is. This is the visible image, and the small blob you are seeing, that is the Orion molecular cloud, labeled as M42, Messier Object 42. But in reality, the cloud is much bigger, and this is what you'll see here. The cloud is as big as the constellation itself. It's not just the central star, but there are a lot of different parts to this molecular cloud. And all of those are labeled so that people have been studying different objects. People have been studying the northern filament. People have studied the Orion Nebula itself. There is on top in the north, there is Lambda Orionis ring. People study those. So we will be concentrating today on the Orion Nebula. And as someone said, what is Sophia? So here is an image of Sophia. Sophia is a plane. It's a 747 plane where we have taken the plane, chopped off one side, and put a 2.5-meter telescope inside. If I show you a cutout of Sophia, this is what it looks like. This is a cutout of Sophia. In the back here is a 2.5-meter telescope weighing about 17-20 tons, which is separated from the front of the airplane by a pressure bulkhead. The light that enters the telescope comes through this Nasmyth tube, and here is where we can attach all our instruments. And in the front of the plane are where people like me who sit and work or observe. Here is what the inside looks like. It's one of our instruments is shown here. This was the instrument used to study the Orion molecular cloud, which we'll come to in a second. This instrument, one thing I forgot to mention is that Sophia is a collaboration between US and Germany. So 80% of the funding for SOFIA comes from US and 20% comes from Germany. And Germany has built one of the instrument, and it's called the German Receiver for Astronomy at Terahertz Frequency. And of course, we astronomers love our names here. So this is called the Great Instrument. All right. So what's a great instrument? It's more like it's more than a infrared instrument. It is infrared, far infrared instrument, but its technology is more like a radio telescope. So it is a heterodyne instrument that looks at the frequencies between 0.49 to 4.7 terahertz, or as I said, long wave infrared radiation. It has different arrays it can use. There is what we call upgrade low frequency arrays, which is 14 pixels. The way you need to think about great instrumented pixel is it's one pixel is a beam looking in, like a pencil beam looking at one region of the sky. So we have 14 of those arranged side by side, and they work in the frequency range of 1.8 to 2 terahertz. There is also a high frequency array, which is a 7 pixels, so they are a bit smaller, but it has a very narrow frequency range, close to 4.74 terahertz. We have 4 grade, which are 4 pixel, but these are co-aligned, so they look at the same region of the sky, but at different frequencies. So there are all different kinds of instrument we use to look at this. So what did the researchers want to learn from Orion? So Orion is a cloud where we have heard for decades that new stars are being born, and there is one big O-type star, like a biggest star that is putting in a lot of energy, and that's what we see as a cloud. What the researcher wanted to understand is how is this star and the gas and dust in the cloud itself related to each other? What are the kinematics? What happens? How does the energy from the star get translated to the cloud, and what happens to the cloud? And they didn't. These researchers just didn't look at Orion Nebula, which is M42, but they looked at 4 other nebula: M43, which is on the north, and then NGC 1973, 75, and 77. So basically, it's a gigantic 1 square degree in size. They studied this whole cloud. And to give you a perspective, our moon is about half a degree. So it's like 2 times the size of the moon. And they wanted to compare the kinematics and physics in these three different regions to figure out what is going on. So here is the data, some of the data I'm showing. The one on the left is from hydrogen alpha. This is what the gas looks like if you look at any night. The middle one is the SOFIA data from carbon-2, and I'll mention what the carbon-2 is. And on the right is the data from carbon monoxide taken using a radio telescope. So these researchers didn't only have the SOFIA data, but they had data from visible all the way to radio. That's how we study clouds these days, because that gives us the most complete picture. But before I tell you, I need to tell you what the C2 emission is. What is this carbon-2 emission? So we'll do a very basic cartoon version of how an atom looks like, how an atom of carbon looks like. So this is how we think. This is, as I said, it's a cartoon version. We have an atom where in the center is the nucleus that contains protons and neutrons, and then we have orbits around the nucleus where you have electrons shown here in blue, and they are orbiting around the proton, the nucleus. So these electrons can be bumped to a higher orbit by throwing in energy, and most of the time the energy comes in a form of a ultraviolet light. So the star is throwing out ultraviolet light, and that light can bump this electron to higher orbits. But that is not the stable orbit for this particular electron, so they usually decay back to the lower orbit. And one of the ways to look at it is shown on the left. So these are the blue lowest line is the lowest orbit, and the upper blue line are the higher orbit. So when an electron falls from a higher orbit to a lower orbit, it throws out a photon. The extra energy that it has when it was sitting there is thrown out as a photon. And that's what we see on Earth. That is the light we see. So if we see intensity of the light, versus wavelength, if we plot, we get what we call a spectrum. And that spectrum tells us that this is carbon that is emitting or oxygen that's emitting, whatever element that happens to be emitting. And we can measure this very accurately in the lab. So we know exactly where these lines appear. And if these lines are shifted, then that tells us that the object is either moving away from us or towards us. Basically a Doppler shift. That's how you detect whether the objects are coming closer to us. If the objects are coming closer to us, then these wavelengths get crushed together and we have smaller wavelengths, which means we are blue shifted. If the objects are going away from us, then these waves get stretched and their wavelength becomes big, and that is red shift. All right. For experts who are in the audience who really want to know all the nitty-gritty detail, here are some diagrams, energy level diagrams that is shown. But today we'll be talking only about the C2 line that is used. This is a width, and here is the data. So here is a composite data of the entire Orion molecular cloud, about 1 square degrees. This shows just one image, but remember this is a spectrum and it's a three-dimensional image. So we have two dimension in sky, the spatial, and the colors basically tell us the third dimension. The red is moving away from us, the blue is coming towards us. One fantastic thing about data like this is because it is three-dimensional, we can see it from different angles. So we can turn it around, rotate it around, and figure out where the material is sitting and how the material is flowing. These are cool as images for public outreach, but here is our real data. This is one of the images that we get. And you'll see that there are these circles. So those are the three regions we'll be studying today. One is the M42, the Orion molecular cloud. The smaller cloud up here is M43, and this one on top is NGC 1977. The data I'll show you today will be just of this region, and then I will generalize it to other parts of the cloud. So once we have the data like this, we can look along the cloud here to see what is happening to the gases and other molecules in the cloud. So here is some data that is shown. So the colors indicate the various molecules that we are seeing. So the green is carbon, that's the SOFIA data. The blue line is CO2, it's a molecular gas, as I had shown before, which comes from radio observations. The purplish here is hydrogen alpha in the visible, and the other two are spars, which are polyaromatic hydrocarbons, and 160 micron is this very tiny grain. So the thing to notice in this plot is most of these emissions seems to be constant till you hit about this place, and that where there is a discontinuity between what is inside the cloud and what's outside the cloud. So the stars that are exciting the gases in this cloud sits somewhere on the left-hand side. And this is the boundary. So if you think the edges that you are seeing here, that edges, especially at here, this one, that edge is this edge that you see in the thing. So using this, astronomers can figure out that what is the temperature of the gas inside, what's it outside. You'll also notice that in many cases, especially C2 line, the green line, the inside it's almost constant, but then it hits the edge, but then it starts to become clumpier. These peaks and troughs basically tell you that we have clumps of gases outside, and it's kind of hot and uniform inside. One of the other way to look at these data is what is called the velocity position diagram. So on the x-axis, I'm basically plotting the distance from the star. So the star is at the center here, and the distance from the star that the gas is emitting. And on my x-axis, I'm plotting whether the velocity of this gas is positive, that's going away, or negative, that is coming towards me. And again, you can use this to find various structures. So since we, as I mentioned, we have three-dimensional data, we can look at different regions. So each of the spectra is an emission of C2 line in different regions of the cloud. And using this, we can build a picture of how the cloud looks like. So the movie that I showed you earlier where I turned the cloud around, we combine all of these data together to make that movie. And then we understand what is the composition of the gas and what is the velocities, whether it is coming towards us or away from us. Okay, and this is one of the images that I'm showing here, where the blue is different velocity. So basically blue, green, and reds are different velocity, and it teaches us more about how the cloud structure is. So this is a very large paper, so I'm not going to show you each and every plots and diagrams that they published, but I'm going to summarize what the results were. So this observation was done using SOFIA in a C2 emission line of these 5 objects mentioned here. That to create this data set, we had 2 million individual spectra, and that's what was stitched together to make that movie. And we compare 3 regions, M42, M43, and NGC 1977. The distinction between these regions is that the Orion complex M42 is powered by a O-type star. It's the largest star. It puts a lot of energy into the cloud, whereas for M43 and NGC 1977, it is powered by a B-type star, which is a smaller star than an O-type star, and it doesn't put in as much energy as the O-type star. But all of these 3 stars are the reason why they are sculpting the cloud and dust around it. It appears also that the M42 is being sculpted by stellar winds. That is the proton and electron that is coming out of the star. That is what is sculpting the cloud of gas. Whereas in M42 and 1977, since it's a B-type star, its stellar wind is not very strong. So it is the gas itself is moving and hitting interstellar medium and glowing. So the one thing that we can find is that most of the gas inside is very hot and it emits in X-rays, whereas outside it is much more cooler and it emits it in infrared. So such structures are usually because these are very young objects. And in fact, the biggest one, M42, is so big now that it still looks very spherical and it has a spherical symmetry, just like the other 2. But soon, another few million years, that's in astronomical terms soon, it's gonna break apart. It won't be circular anymore. It will change. And yeah, so that's what I have as far as looking at the Orion molecular cloud using SOFIA. So thank you very much for listening, and I'll take your questions now.
Well, thank you so much. That was wonderful. And so cool that you're one of the investigators of that data. So we have that personal connection. Yes. We have a very important question from Addie, age 8, who wants to know what happens to stuff when it gets sucked into a black hole.
Whoa, I don't know. Like, why are you asking me? No, the thing is, we don't know. So all we can see is what astronomers talk about, the event horizon. That is the horizon. If you look at the direct image of black hole that I showed you, it had that black horizon. So whatever is outside that horizon, we can see, we can measure, we can detect. But once the object goes into the black hole, for all practical purposes, we don't know what happens. I mean, it goes into the singularity. Now, you'll hear this term singularity thrown around for black hole, but basically what it tells you is that so the way astronomers studies the universe is mathematical. So we have equations and we find solutions for that, and that's how we understand the universe. But in black hole, at that point, singularity, all our equations break down. That's what singularity means. Our equations or our solutions to the equation goes to infinity, which means we don't know. So that is an unknown. So what happens to a thing when it falls into a black hole? Sincerely, I don't know. And that's, who knows, maybe we will invent some math or some things to understand what happens in the singularity. But as far as now is confirmed, material that goes into the black hole just goes right into the singularity, and there all our physics equations break down and we have no idea what happens.
All right.
I
And I'll
don't
just
know
add,
if I answered your question satisfactorily or not, but that's what it is.
I'll just add that all of the black holes are very far away, so don't worry.
Oh, yeah, that's the other question. I'm gonna answer a question I have not got, but I think people tend to ask this. People are worried about black hole. It's like, oh, will we get sucked into it? No, you won't get sucked into it. For example, tomorrow, if our sun turns into a black hole, which it cannot because it is very less massive, but if it did, Earth wouldn't even feel it because the gravity that Earth feels from the sun would still be the same. The sun would have shrunk in size, but the gravity field from that mass would still be the same. So we would happily be going around a black hole. Of course, we won't have sunrise and sunset. It'll be dark throughout the year, but we are not going to get sucked in. The reason the cartoon you saw where the star broke apart and sucked in, that was because it got very close to the event horizon. When that happens, then material will get sucked in. But anything that's outside, it will just orbit, just like how I showed you the movie about the star orbiting our central black hole in the center of the galaxy. They'll just keep orbiting around there for millions and billions of years. Nothing is going to happen. Next question.
Good. So you mentioned that there's supermassive black holes in the middle of galaxies.
Yeah.
Is that true of every galaxy? And does it relate to how the galaxies form?
That's what is the belief now. So for the longest time, there were detection of one or two, but with the survey called SDSS, Sloan Digital Sky Survey, they looked at thousands of galaxies and almost all of them seems to show that there is a supermassive black hole at the center of those galaxies. So I think that statement is correct, that most of the galaxies have supermassive black holes.
All right. And is that part of how galaxies form, or?
It's a one facet of how that galaxies are formed. There is still research about understanding how that black hole formed itself. So that is not at solved, just because we don't have enough data for detailed data for each of this. So it is a part of an evolution of a galaxy, but we don't know exactly how.
All right. And
one more thing, I keep saying we, doesn't mean I'm the one doing the research. I'm just saying we, the scientists, we, the big we. So it's not that I physically do this research. I'm just curious, interested, and want to learn more about it. Okay, next question.
Could be a call to action to all of you out there as well. If you want to be part of this,
Right.
You can get involved. So how many different types of stars are there? Like there's type O, type B, etc. How much of the alphabet are there in star types?
We have categorized star about 8 or 9 different categories, depending on their mass and depending on how bright they are. So those are the stars we talk about, O, B, A, so on and so forth. So there's about 9 different categories. But there have been recently a couple of, I think 2 categories added because we had not yet detected really small, faint brown dwarfs. So once we discovered that, I think we have 2 more. So I would say about 9 or 10.
All right, 9 or 10 different types of stars so far.
So far.
Depending on what else we find. So let's see. We've got lots of questions about primordial black holes, which you talked about a little bit. We need more data, please, to answer those questions. How many black holes might there be? Let's narrow that down in our galaxy.
Again, there is no certain answer, but if we believe some of the models that we have, there should be about thousands of them at least, intermediate mass black holes floating around in our galaxy. We have detected only about a handful of those, like a dozen or so. So there's a lot of them out there, but as I said, the problem was that it's really hard to see them because they're just floating around in space. And once in a while, their path may cross a star that is close by and light up in X-ray optical, and then we can see that. But the feeling is there should be about thousands.
Thousands of black holes. All right, but again, They're not coming to get you, so don't worry. So what is Sophia going to look at next?
Sophia is doing a lot of things. What I said is just a very tiny part of it. Sophia flies 4 times a week, so we are seeing a lot of things. The Sophia is like any other observatory. What that means is any astronomer from the world can apply for time on Sophia. So the way the astronomy works is think of any big telescope, whether it's the telescope on Hawaii or the space telescopes. What astronomers do is they apply for what we call time. So they say, this is the project I'm going to do. These are the aims. This is how I'm going to get the data. These are the analysis I'm going to do, and this will be the publication. So they write this proposal and hands it in to the people who maintain the project. They convene a committee of experts from the community, that is from all astronomy, and the panel decides the ranking of various proposals that you get, and they award you time to observe on that telescope. So basically, what Sophia is going to observe next, whatever the astronomers are curious about. But since Sophia is an infrared telescope, most of the studies will be about understanding gas and dust physics in various places, like molecular cloud, in debris disks. Sophia also has a polarimeter on board, so we can measure the magnetic field of various clouds. So that's a huge area of research in the near future. So there's a lot of different things Sophia looks at. Sophia looks everywhere from planets to our moon, all the way to the center of our galaxy and other galaxies. So yeah, it's keep an eye out for on our website, sophia.usra.edu, and as the research gets published, you'll see the new updates there.
All right. And for those of you who weren't familiar with Sophia, I encourage you to look up some of the images, because Sophia has put out some really gorgeous images of space. And so we have some more questions about Sophia. How far away can Sophia see?
I get this question a lot, not just with Sophia, but with any telescope. And unfortunately, so astronomers and scientists in general are very picky. They take a question and start to rip it into pieces to try to find a solution and answer. So I'm going to do the same thing. Sorry, I'm an astronomer. I can't help it. But usually the question is not about, at least in astronomy, it's not about how far a telescope can see, but how bright or how faint can a telescope see. Because how much faint you see depends on the size of your telescope, the light gathering power of your telescope, and the instrument that's on board. And I'll tell you why I won't talk about the how far. So imagine something that is very small but quite bright, and that is close by, and you may see that. But there could be objects that are really big but extremely faint, and that's closer, but you won't see it because it's not bright enough. So it's the brightness is what we are detecting. So as I said, Sophia has looked at galaxies that are millions of light years away from Earth. So I think the question is how faint you can see, and depending on different instrument, how faint we can see changes.
All right. And also about Sophia, what airport does it fly from? Where is it based? And where does it fly when it flies?
Maybe I should just give a different talk on Sophia. So Sophia is based in one of the NASA centers, and the name of this NASA center is called Armstrong Flight Research Center. It's in Palmdale, about an hour away from Los Angeles. So that's where the plane is. And the science center where we all work, scientists work, is in NASA Ames Research Center, which is in Bay Area, near Mountain View in California. So every night, Sophia flies from Palmdale, and because it's a plane, we can fly wherever we want, but there are some regions we can't because of military or because of different countries. For example, we can't go too much south because south of us is Mexico, and we don't have permissions to fly into Mexican airspace. But in the north is Canada, and we have permissions to fly there, so we can go anywhere. So Most of the time, Sophia flies out of Palmdale and it goes all over the place, over the Atlantic, over the Pacific, over the continental US. And in summer, that is our summer, we go down to New Zealand because for them it is winter and observing in winter is the best. So we go to Christchurch, New Zealand, on the Southern Islands, and we fly 2 months out of there.
Interesting. Why is it better to observe in the winter?
Winter that so one of the reasons we use Sophia is that if you sit on the ground and try to look at the infrared universe, you're not going to see anything. And the reason you're not going to see anything is the infrared light, or infrared is basically heat. So the light or heat coming out from space is absorbed by the water molecule in our atmosphere. So the higher we go, the less water it is. So in winter, what happens is because the temperature is so cool, the water molecule tend to float down. So whereas in summer it is hot and the water molecule tend to float up. So when we fly Sophia at around 43,000 feet or 41,000 feet, even in summer, if we fly from say Palmdale, then we'll still have a lot of water above us, above 43,000 feet. But if we do the same thing from New Zealand, then most of the water would be below us. So it's basically trying to get as high as possible, but avoiding all the water. Does that make sense, kind of?
Yes, it totally does. That's so interesting. I'd never thought about that. We have another question from Callaway, age 7. How big is the biggest black hole in size, not mass? Like the event horizon.
I wouldn't know. I wouldn't know off the top of my head. I'll have to look that up. I know there are black holes that are billions times the mass of the sun in the center of our galaxies, and most of them are almost smaller than our sun. The size of the event horizon is usually smaller than our sun. So it's very close region, but the exact number, I don't know. I'll have to look it up. So if you email me sometime, maybe I'll look it up and we can talk on email.
And just to add to that, one of our astrophysicists at the museum recently calculated if a black hole had the mass of the Earth, it would be about 1.7 centimeters is how big the event horizon would be. So teeny tiny. And how about nebulas? How big do nebulas get? And also,
depends. Nebulas can be large. For example, the one I showed you on Orion, that's one of the biggest. We have another nebula that we observed, which is in the constellation of Taurus. Those are large too. These can be, I would say, I don't want to say it in parsecs. And if I do light years, like hundreds of light years across. You can have nebulas about hundreds of light years across.
Wow. So big, very big.
But it's a bit complicated because these are dynamic structures. So something that exists today may not, because they'll change. They will evolve, like nebulas fall down and become stars, and then stars may go supernova and then destroy the nebula, like it's doing in Orion, for example. The star is basically breaking the nebula apart. So a nebula that's today, which maybe, I don't know, 10 light years, in a million years, it won't be, because it may have broken apart or it may have evolved into something different. So one has to always remember that these are dynamic events. These are not static events.
Interesting. Yeah. Must be hard to decide where the edge is at some point.
It usually is.
So we're getting down to the end of our time. If you have any final questions, please pop them in the chat. If you need to go, we understand it's a school night. Thank you so much for joining us. And thank you so much, Dr. Shenoy. This was such a wonderful presentation.
Thank you for having me. This was great.
Of course. And we hope you can all join us next month. October 27th is the next 60 Minutes in Space. And we'll have a guest presenter, Dr. Graham Lau from the Blue Marble Space Institute of Science. All right, and we're seeing some thank yous. Somebody looked up the biggest black hole. It's about a third the size of our galaxy. Very big. Okay. And so, yeah, thank you so much, everyone. And any final thoughts, Dr. Shenoy?
Nope, as I said, this was great. I love doing this. So hopefully I'll see you again sometime in the near future. And yeah, keep your questions coming.
All right, wonderful. And again, thank you everyone for joining us. Have wonderful evenings, and look up some Sophia images and keep your eye on Sophia news because very cool stuff and incredible pictures. And you've now met one of the scientists who investigates all that data. So thank you so much. Have a wonderful evening.